All right, so I'm going to just go ahead and write these two at the top. Okay, y equals, and if you want to transfer them over to this page, okay, it'll be easier than to have to keep flipping from page 1 to page 2. All right, so what you're going to do is start at -1, go up 2 over 3. Okay, you could also do a double negative, down and left. Okay, then you would connect those together. Okay, and then the second one, you start at +4. Okay, and then I'm going to go down 1 to the, down 1 again. Okay, and you can tell that that will actually cross right there. So then you would just read the coordinate where the two lines intersect. And what coordinate is that? All right, so they intersect at 3, 1. And write that right on the graph for me. Okay, 3, 1. So if you go back to page 1, and of course mine is sideways, but you'll see 3, 1 is right here. Okay, so that's what you're doing on pages 1 and 2. So I would not count this, like I said, completely new lesson, except for you're putting two lines on the same coordinate plane, because that's what a system of equations consists of. Now notice some of these equations up here, you do have to solve for y. So all of them have not been solved for y for you. Questions 1, 2, 3, part of 4 has been solved for y. So you do need to make sure you're putting those in slope-intercept form before you graph. Okay, any questions just on part 1 of the lesson? Because there's one answer up here that says no solution. See this one right here? It says no solution. How would you get a no solution type of equation? So if I graph two lines and I get a no solution, what do you think those lines would look like? They don't intersect. So what type of lines do not intersect? What do we call those lines? Parallel lines. Very good. So now, what do you know about parallel lines? Parallel lines have the same what? Slope. Very good. So when you solve these and you see something that says y equals 1/2 x plus 3 or y equals 1/2 x plus 4, both of them have 1/2 as the slope, you already know the lines are going to be parallel. Okay, but you're going to graph it still, and then that type of answer would be a no solution type of answers. Okay, because lines that never intersect will not have a solution, because the solution point is considered where the two meet. Okay, so when I ask you, like if we go back to the one that we just did, and I say, what is the solution to this? Then I'm asking you, where do these lines intersect? Okay. All right, so there are 3 different possibilities that you can have then for a system of equations. 3 different types of answers. One answer would look like this, where they actually intersect and you read the coordinate. One answer would be if the lines are parallel. So you're not going to draw this. I'm just going to draw some parallel lines. Okay, so that would be what we call a no solution. Okay, but don't put this on your paper. You're just looking right now. And then the last type would be a line like this, where you graph the same line over top of one another. Now that will be what we call all reals or infinitely many solutions. Okay, so those are the 3 types of answers you could have, where you graph the same line twice. So that means they're intersecting everywhere. So that's infinitely many solutions. Or if the lines are parallel, no solution at all. And if they actually intersect, then you have a solution. One solution, that is. Okay?
We have seen several types of geometric relationships that can exist when 2 linear equations are simultaneously graphed. Simultaneously graphing systems of equations like this is often a helpful tool in analyzing physical and mathematical relationships. In particular, the points of intersection of two graphs have a special significance since the intersection points represent common solutions to both equations. To illustrate this concept, let's look at a race between a tortoise and a hare. As the race begins, the hare, engrossed in a fascinating chapter in his algebra book, decides to give the tortoise a head start so that he can finish reading the chapter on solving systems of linear equations. As the race begins, the tortoise starts down the road at 1/2 mile per hour, a very brisk pace for a tortoise. We can graph the tortoise's distance from the starting point as a function of time, letting the vertical axis represent distance and the horizontal axis represent elapsed time. We see that in the beginning, when the elapsed time is 0, the tortoise's distance from the starting point is also 0. After that, since he is traveling at a constant speed, his distance increases linearly as a function of time. Since the tortoise's speed is 1/2 mile per hour, after 4 hours, he has traveled 2 miles. 4 hours after the race has begun, the hare finally finishes his algebra chapter. Even though the tortoise has obtained a significant head start, the confident hare decides to take it easy. Since he knows that even casually strolling at 2 miles per hour, he will eventually pass the tortoise. So 4 hours after the race has begun, the hare is still 0 miles from the starting line. But from this point on, he travels at a constant speed of 2 miles per hour. Since the hare travels at a faster rate than the tortoise, the hare's graph has a greater slope. Looking at these two graphs, we see that throughout the race, the tortoise's distance increases linearly with time. And after 4 hours of elapsed time, the hare's distance also increases linearly. Until at some point between 5 and 6 hours after the race has begun, the hare and tortoise meet. The point where the two graphs intersect represents the instant at which the tortoise and the hare are at the same place at the same time. If we can create equations for these two graphs, there are mathematical techniques which we can use to determine the coordinates of the point where the two graphs intersect. Knowing these coordinates, we can then determine the exact time and place where the tortoise and the hare meet. To create an equation for the tortoise's distance as a function of time, let's use the variable x to represent the time coordinate and y to represent the distance coordinate. We saw in the chapter on solving motion problems with linear equations that if we graph distance as a function of time for an object traveling at a constant speed, the slope of the graph will be equal to the speed of the object. So the slope of this line is 1/2. Since we know that this graph intercepts the y-axis.
Why do you keep that around your neck? It's not a necklace.
We can use the slope-intercept form to write the equation for this line. The value of the constant m in this equation is the slope of the line 1/2. And the value of b is the y-intercept, 0. Eliminating the 0, we see that the equation for this line is y equals 1/2 x.
Isn't that direct variation?
Now that we have the equation for the tortoise's graph, we need to derive the equation for the hare. Since the hare is traveling at a constant speed of 2 miles per hour, the slope of his graph is 2. We don't know the line's y-intercept, but we do know that the line passes through the point 4, 0. So we can use the point-slope form to write the equation for this line. Filling in the values for the constants, we replace x1 in the equation with 4, y1 with 0, and m with the line slope 2. We can then simplify the equation by eliminating the 0. and distribute the 2 to the terms in parentheses. Multiplying 2 times 4 to get 8, we see that the equation for this line is y equals 2x minus 8. We now have equations for the tortoises and hares' distances as functions of time. It is important to remember that although the lines described by these equations extend infinitely in both directions, only the portion of the lines whose coordinates are positive are meaningful in this particular example. If we can now use these equations to calculate the coordinates of the point where the 2 graphs intersect, we will be able to determine the exact time and distance where the tortoise and the hare meet. In the next lecture, we will introduce a technique called substitution, which will allow us to calculate the unique coordinates which simultaneously solve both equations and thus find the intersection point of the 2 graphs.
All right, which is actually our lesson. Okay. All right, so what we're going to do is actually that. We're going to use all our skills that we know for solving equations, but we're going to be using a different method called the substitution method. Okay, so take a look on page 3, and we're going to, and we could definitely figure out the tortoise and the hare's problem, but I'm going to start off with first, and we'll come back to the tortoise and the hare equations just to get, an answer for that. But let's look at page 3, and we're going to do question that one that says you try, okay, because the example is already done, but there are steps off to the left that you can go back and read later, but I'm going to walk you through what you're going to do. This method is called substitution, so that means this is done all algebraically. The method that we just did a few minutes ago, we call that the graphing method, for obvious reasons, because you graphed. So this method is called substitution. So what do you think we're going to be doing? Substituting. Okay? So that's why it's called substitution method. So just like the graphing method, you were graphing and then you saw where the 2 lines intersect. So this is done all mathematically. So let's take the 2 equations. These are the 2 that you have written on page 3. And the very first step is, and this is where you got to pay close attention, because if you miss the first step, then everything else is just going to go right on out the window. So the very first step is to take a look at your equations very carefully, both equations. And you're looking for variables that have coefficients of 1. So all of those have a coefficient of 1. Now, I would probably say most of the time you would at least have one coefficient of 1 in one of the equations. So let's say you don't have a coefficient of 1. Then you just got to choose one, all right? But a good rule of thumb is always to look for coefficients of 1. And the reason is because then when you solve for one of these variables, you're not dealing with a lot of fractions, okay? So I'm going to just choose one of these to solve for. So I'm going to solve for y in the very first one. So this is the one I'm going to solve for, y. You can solve for x. You can solve for the other y. You just choose one to do. Okay, so the choice is yours at the very beginning as to which variable you want to isolate. You have to isolate one of them. That is step 1, right? So since I'm going to isolate y in the first one, I just need to move the x term to the other side. Is that correct? So how do I get the positive x to the other side? I just minus it to the other side. So that I'm going to end up with y equals negative x plus 10. So I just moved it to the other side by subtracting it over. So that's step 1, right? Step 2 is, and now you guys know another name for equals is. Is that correct? So now this is saying y is now negative x plus 10. Okay, so y is no longer called y, it's called negative x plus 10. So where I see y in the other equation, it is now going to become negative x plus 10. Okay, I'm going to substitute it with negative x plus 10. So I'm going to bring down the 2x, that's not changing. Okay, then I'm going to bring down the plus sign, but then I'm going to put the substitution part in parentheses, which is negative x plus 10, because that's what y is called now. And then equals 15. So that's where the substitution method comes in. So I'm substituting y for being negative x plus 10. So see if you have a question on that. Because the rest is just solving. Just like once we get the substitution done, the rest is just solving an equation. So technically, this is 2x minus x plus 10 equals 15 when I drop the parentheses. So now I'm going to combine the 2x minus x. So when I do 2x and I take away an x, I'm left with x plus 10 equals 15. Solve for x, and like I said, the rest is just solving an equation. So x equals to 5. So once you do the substitution, then you're ready to just solve that equation. So of course we need to have an x coordinate and a y coordinate. So now what I found out from this, that x is 5. Okay, that's what I'm getting from what I just solved. So now x is 5. Okay, so where do you think I'm going to substitute that into? I'm going all the way back where step 1. Remember I told you step 1 was very important, where I isolated y. Now I know the value of x. Okay, what is x again? X is 5. So where I see x here, I'm going to substitute the value of 5. So this will be y equals, and then I'm going to put 5 plus 10. So what is negative 5 plus 10? Actually comes out to be 5 as well. So now I have my x and I have my y value. So if we were to graph this, then this line would have intersected at the coordinate 5, 5. You do need to write your answer as a solution at the end. So just don't leave x by itself and y by itself. At the end, you do need to write it as a coordinate. Okay, so that's doing all of the work algebraically without having to graph the lines. Okay. Now, if you weren't sure these answers were correct, you could actually put the values in for x and y into the original problem. Okay, what's 5 plus 5? 10. Then you could do the same thing down here. 2 times 5 is what? 10. 10 plus 5 is what? 15. That's how you can check it. Okay, because you really do need to know how to check a system, and all you do is replace it back into your original equations and see if it checks out to be correct. All right, let's move to the next page. Page 4. Okay. So on page 4, still using the substitution method, I'm going to do the u try 1 and then you'll do the u try 2. So I have y equals 2x plus 8 and y equals 5x minus 1. Now notice step 1 is already done. Okay, how do I know that? Because they've already isolated one of the variables. So I put up here step 1 is completed. Okay, step 1 is already completed because they have already isolated. Actually, they isolated the same variable in both problems. So you might say, well, which one do I substitute? It doesn't matter. Okay, so I'm just going to say, I'm going to put a square around that one because that's my step 1. I chose to use that one as my substitution. So where I see y here, I'm going to substitute it with 2x plus 8. Everybody with me? All right, so we're going to replace y with 2x plus 8. And then we write the 5x minus 1. And now the rest is just solving an equation that has variables on both sides. So you guys know how to get all your variables to one side. Okay, go ahead and solve it from there. All right, so I got x as 3. So remember, I put a square around my step 1 because I want to know where to go back to when I'm finished. So now I know x is 3. So where I see in my step 1, I'm going to replace x with 3. And always put your substitutions in parentheses. So I'm going to have y equals 2 times 3 is 6. 6 plus 8 is what? 14. And then don't forget, you write your final answer as a coordinate. Okay, so don't get all the way to the end and then not put them together. Okay. All right, so you're going to do the try to. So if you want to like put a square around the first one, and that's what you're going to substitute into the second one, okay, I'm going to let you guys give that a try and see what you get. Okay, so if you got the same answer, 314, we're going to move on to page 5. Okay, so if everybody could move on to page 5. Okay, I'm going to do the you try 2 this time, and then you'll do the you try 1. So we're on page 5. All right, so here are my 2 equations. Actually, that should be a 3. All right, so step 1 is not done for me this time. I have to isolate one of these variables. And what did I tell you guys to look for? Coefficients of what? 1. So this is the only one that has a coefficient of 1. So obviously that's the one I'm going to solve for. Okay? Always look for coefficients of 1. So if I solve this one for y, that means I need to add the 2x to the other side. Is that true? So I'm going to end up with y equals a positive 2x plus 4. Okay? So now y is called 2x plus 4. That's the name of y. So where I see y here, I will replace it with 2x plus 4. So 3x minus 2, parenthesis, 2x plus 4. There's my substitution, equals 6. Okay, are we together with that step? So I isolated y in the first one by adding the 2x to the other side. And I just substituted y in the second one to be 2x plus 4. Now we're just going to work it out. So 3x, distribute this negative 2. That'll be minus 4x. And then a negative 2 would be a minus 8, because you're distributing a negative 2 to the 4, equals 6. So what is 3x minus 4x? Negative 1x. All right, so negative 1x minus 8 equals 6. What do I do after that? Add 8. So what does that give me? Negative 8 equals to what? 14. And then what do I do then? Divide by the negative. So x equals what? All right, so we got negative 14 for x. So what do I do with that? Here's my step 1 right here. So what do I do with that where x is negative 14? Substitute it back in for x. Very good. So I'm going to have y equals 2 times negative 14, okay, plus 4. I'll have to squeeze that in. So 2 times negative 24 is negative 28. What's negative 28 plus 4? Negative 24, is that true? All right, so my coordinate or my solution is negative 14, negative 24. Okay, negative 14, negative 24. Okay, just make sure you write it as a solution point. Okay. All right, so you're going to do the one that says you try 1 on page 5. Okay, see what you get. Your answer and see if you get 5, negative 11. Okay, are we okay with that? Okay, all right. Okay, so